the resolution of our ultrasound devices is about the same as the wavelength. Remember that our wavelength was related to the frequency by the speed. The speed of your wave is equal to the frequency times the wavelength. So if I have a frequency of 3 million hertz and a speed of sound of about 1,500 meters per second, now that's the speed of sound like through your body, which is largely water, mostly water, so faster than it travels in air. So with that, the resolution is about 0.0005 meters, or about a half a millimeter. You know what a millimeter is? You get your ruler, on your ruler on the centimeter side, it's the smallest marking. It's a thousandth of a meter. So a half of a thousandth of a meter. Probably about the width of your pencil lead. That's about a half a millimeter. That's pretty amazing that you can get that kind of resolution, which allows you to diagnose things in infants before they're born, or in adults in their joints and what have you. So this can also be used to heat the tissue for restorative purposes. And I think you athletic training majors, you do that as well. Is that right? You use ultrasound machines to help people heal from injuries. Ablation of cancerous tissue. And for breaking up kidney stones. So like the breaking up kidney stones, they send a very high frequency sound wave, and the energy from the sound wave will actually break up those kidney stones and allow them to pass through your system uh, with less pain, at least, than if they were bigger. All right, let's try a couple of these little clicker questions. You stand 1 meter from a point source of sound and the intensity is I. If you move to 2 meters away from the point source, what is the new intensity? Now remember, our intensity is given by this equation. I is equal to the power divided by the area. And so if I have my source of sound here, I'm 1 meter from it. The intensity is a certain amount, or 2 meters rather. On 1 meter, and what happens if I move to 2 meters away from that source of sound? What happens to the intensity? Is it the same? Is it twice, 4 times, a quarter, or half the original intensity? Okay, good. Y'all are doing a good job in that you've realized, I think everybody, last I looked, everybody realized that it's not going to be the same, and of course it's not going to be louder. So all of you have chosen either D or E. And it is either D or E. That's going to be the answer. It actually will be less intense. Excuse me. So now you need to decide which is it going to be. This is a good practice for multiple choice exams, by the way, that you remove options. And often you'll be able to remove 2 or maybe even 3 options. So ask your neighbor what they put. Did they put a quarter of the intensity or half the intensity? It is one of those answers. Right now you're roughly split on that. But ask your neighbor, please ask your neighbor what they put. Or tell your neighbor. I don't hear much telling. Remember how the area is related to the distance from the source, and that will help you in determining the answer. All right, I'm going to stop at 207. 207. Okay, good. D is right. It is a quarter of the intensity. The reason is because this area is power. The power is going to remain the same. The source is still sending out the same amount of energy per unit time, but this area is 4 pi r squared. So if I increase the radius by a factor of 2, which is what I've done, then I've decreased the intensity by a factor of 4 because they have this inverse square relationship. If I double this, I quarter the intensity. Oh, and by the way, did y'all know today is, what is today? You might know? It's Friday, yes. Because it's, March 14th, 3.14 at 1:59 this afternoon. You're supposed to eat pie or something. I don't know. All right, let's try this next one. Damage to the cochlea is usually the result of which of these? Some of these might be correct, but there is one that it's usually the result of. All right, let's stop at 35. Okay, good. D is right. Some of you put A, B, or C. It could be either A, B, or C, but really the most common thing is that you actually lose those hair cells in your cochlea. Remember, the cochlea is this big, long, fluid-filled chamber. It's twisted up like a snail, but it's this long, fluid-filled chamber. Which is it? The stapes pushes on the basilar membrane, and so if your basilar membrane is perforated, then that's bad, but that's not usually what happens. The stapes pushes on the basilar membrane and transfers the vibrations into the fluid of the cochlea, and those vibrations will resonate with the hair cells. Now, if you have excessive noise or you have, sometimes people have genetic issues or diseases that cause them to lose their hair cells or they just never had them, then that can affect your cochlea because of the hair cells. Those hair cells actually resonate with the sound and send an electrical signal to your brain. So D is the right answer there. All right, let's look at these. We'll do the top left one here. Intensity is defined as which of these? All right, we'll stop at 30. Okay, awesome. It is the power over area. Why did the boy eat his homework? The teacher said it was a piece of cake. Have I told y'all that one? I don't know. Okay, good. Well, let's try this one on the right. Which of these is the lowest intensity of sound a person can hear? All right, we'll stop at 28. 28. Okay, good. C is right. 10 to the minus 12. That's your threshold for hearing. Uh, and now, how about this one, the one on the left? 50 decibels is how many times as intense as 30 decibels? All right, we'll stop at 25. 25, or 30 rather. Okay, good. C is right. Remember, every time I have an increase of 10 dB or 10 decibels, that is a multiplication of 100 times the intensity. So where I have 50 decibels, which is 20 more than 30, the intensity of the 50 decibel sound is actually 100 times the 30 decibel sound. If this was 30, if this was 60 decibels, it would be 1,000. If this was 70 decibels, it would be 10,000, and on and on. An increase in 10 dB causes an increase in 10 times the intensity. If I add 10 to the decibels, I multiply 10 times the intensity. It's a logarithmic scale. Let's see. Did y'all do well on it? Was that a joke question? It was. Okay. Do you know what the great thing about Switzerland is? I don't know, but the flag is a big plus. All right, let's try the noise canceling headphones. They operate because of which of these? All right, let's stop at 30. Okay, awesome. It's the interference of sound waves. Remember, those noise canceling headphones, they detect the sound that's out about in the world, and then they create a sound that's exactly the inverse of the noise that you hear out there, and that causes it combines those sounds when they interfere or those sound waves combine. They they cancel one another out. That's why they're called noise canceling headphones. They don't muffle the noise. They don't select it out in any way. They just generate another sound that cancels it out. Let's see. So if helium walks into a bar and a bartender says, "Hey, we don't allow noble gases in here." Helium doesn't react. This is a noble gas. Y'all get it? All right. Let's see. I think that's the end of that chapter. Yeah, so we're going to move on to electrical properties and cell potential. We'll talk about a lot of different things in this chapter. We'll talk about potential. If you've had, some of y'all have had anatomy, you've talked about potentials, action potentials, graded potentials, stuff like that with the neuron. You know, is anybody? Yeah, shout out to action potentials and graded potentials and all that business. So we'll see that. We'll talk about the cell as a capacitor. A capacitor is just two charged plates, and we'll actually look at capacitors and see how they operate like in a circuit. We'll talk about resistance, that is devices that resist the flow of electricity. We'll also talk about fields and potential. I said potential. We'll talk about fields as well. The basics of charge. Let's see. We'll talk about some things that have to do with electricity, not in the body, but things that are associated with the body, like the body scanner, like they have over at the rec center, that sends electricity to your body. You can use certain devices. Scientologists do this, but certain devices to send electricity to your body and sort of gauge your psychological response to things. Gauge if you're nervous or not. So we'll look at that as well. So kind of an interesting chapter. Sometimes the topics students find to be difficult in this chapter because sometimes potential and fields, those are kind of abstract ideas and they're sometimes difficult to understand. But we'll be okay. We're going to go through and I'll be patient and you'll be patient with me too, I'm sure. So let's look at electric charge. It is a fundamental property of matter. Along with mass. So all matter has mass, all matter has charge as well, because we're made up of charged objects. We're made up of electrons and protons. We got some neutrons in there too, which have neutral charge, but we're made up of these charged materials. So all bodies have a measure of charge in them. The fundamental unit of charge, which we call 1e, it has a unit of coulombs. And 1e has a value equal to 1.6 times 10 to the minus 19 coulombs. This is the charge of an electron and a proton. So an electron has a charge of this value, and so does a proton. Of course, an electron has what sign of that charge? Is it plus or minus electron? You know, it has a negative charge. A proton have the same charge, but it's negative. The proton and electron, they're different masses, but they have the same charge. In fact, the proton is about 10,000 times the mass of a proton. I mean, of an electron. Did you know that? Proton is 10,000 times the mass of an electron. We say that charge is quantized. And what that means is that charges come in particular quantities. So for example, um, I can have 2e, right? And that would be 3.2 times 10 to the minus 19 coulombs. I can have 3e, and that would be 4, sorry, this should be 3.2, not 3.6. I can have 3 times the fundamental unit of charge, and that would be 4.8. That's just 3 times 1.6 is 4.8 times 10 to the minus 19 coulombs. But I cannot have, say, 2.4 times 10, or not 2.4. Let's see, let's do, I cannot have 3.9 times 10 to the minus 19 coulombs. That's not allowed, because that would mean that I would have some fraction of an electron or a proton. And as far as we're concerned, we'll say that the electrons and the protons, they cannot be split up. That is a fundamental unit of matter, and you cannot split it up. So I can have 2e and I can have 3e, but I can't have like 2.5e or 2.8e. I can't have anything in between. I have charge that is in these very discrete quantities. The charge of one proton is 1e. I already said this, but a charge of one electron is minus 1e, and the charge of one neutron is 0e. All atoms have charges, but most are typically neutral. All right? Do you understand what I mean by that? That every atom has charges that make up, the periodic table of elements. But most atoms in the world are in a neutral state. That means they have equal numbers of positive and negative charges. So we would say if we look at them, it's like their net charge is 0. So when I say that they're neutral, that means they have equal numbers of positive and negative charges. Cations are positive, and anions are negative. So a cation is one that has too few electrons, and an anion is an atom that has too many electrons. Cations are positive, anions are negative. This will be important when we talk about the nervous system and how that works, because we'll talk about how these different ions travel back and forth between the cell membrane. And so we need to know which are positive and which are negative. This one has too few electrons, and this one has too many electrons. And there are a number of chemical processes by which that can happen, where you can strip away an electron, or you can add an extra electron to an atom. Atoms become charged by the removal or addition of electrons, not protons. And that was something that was not understood for a long, long time, up until, I guess, gosh, what, beginning of the 20th century, maybe? No, before that, I think. But not that long ago, people didn't know this, that how the atom was made up. And we'll talk about some different models of the atom. But today we know that when we have an atom that's charged, that is, it's a cation or an anion, it is that way because of you've altered the electron states. You've taken an electron away or you've added an electron. But you can't really change the nucleus very easily. But we'll talk about how in the next chapter, or in a couple of chapters, with nuclear processes, how you can change that through the process of fission or fusion or decay. Um, Charge is quantized. I mentioned this earlier. Um, that is, it comes in particular quantities, plus or minus 1e, plus or minus 2e, plus or minus 3e, and on and on. You can't have plus or minus 1.5 fundamental units. Make sure that you're clear on how I'm using these letters. When I use e with no superscript, that's just the fundamental unit of charge. But when I talk about electrons, I'll do an e and then I'll put a negative superscript. That's an electron. Sometimes when you talk about protons or other cations, which are positive, you'll do an e with a positive superscript. All right. So E here refers to my fundamental unit of charge. E with a negative is an electron, and E with a positive is a proton or sometimes a cation. Conservation of charge. We do not produce or destroy charge. We simply move them around. All right. Let's try some of these. Just see where you stand. A positively charged atom is called what? A pion, an anion, a cation, or a gluon. What is a positively charged atom called? All right, let's stop at 30. Look at y'all. So why did the tomato turn red? It's all the salad dressing. Which of these is not a valid charge? Think about our quantization of charge. All right, about 7 of you have the right answer. Feel free to turn to your neighbor and tell them what you put. All right, I'm going to stop at 57. 57. Okay, good. I noticed that a lot of you put B. Uh, B has a negative, and so we haven't really, shown these with negatives, but this number represents what types of charges? Well, first of all, we said it says 3.2 times 10 to the minus 19, and so we know that our fundamental unit of charge is 1.6 times 10 to the minus 19. These cancel out, and 1.6 will go into 3.2 twice. 2 times 16 is 32. So this represents 2, what, protons? No, 2 what? Electrons, right. So B is a valid charge. It's negative because it represents the charge of 2 electrons. This represents the charge of 3 protons because 4.8 over 1.6 is 3. 3 times 16 is 48. This represents 1 proton, but this represents somewhere between 4.8 and what? 6.4, somewhere between 3 and 4 protons. So D is not the right answer because if I try to divide 5.2 by 1.6, I get a remainder. I don't get an integer number. So D is the right answer here. All right, let's look at electric force. We observe electric forces between two or more charges, forces always require at least two bodies, right? We talked about this with regards to Newton's third law, that if ever I have a force that is acting on something, then I must have an equal and opposite force. And this Newton's third law, like, it might have made sense when you're talking about touching things, because when you touch something, you have two bodies involved, like you have the hand and the wall, and the hand exerts a force on the wall, and the wall exerts a force on the hand. But with Coulomb's law, it begins to get kind of far out there, like, because I have these forces that are acting upon one another. Say, for example, I have Q1 and Q2. Let's say that this one is positive and this one is negative. I have a force acting on both charges. This is the force on particle 1 due to particle 2, and this is the force on particle 2 due to particle 1. And we know from Newton's third law that these two forces must be equal and opposite. That if I have this force, there must exist another force out there in the world that is equal and opposite. And the force that exists is this force. It is both equal and opposite. But notice these charges, they're not touching. Right, we saw this with gravitational forces. Gravitational forces are also a type of field force. That is that they don't require contact. Coulomb's law describes the magnitude of this force. It's K times Q1 times Q2 divided by R squared, where R is the distance between the two charges. K is a constant. It's called Coulomb's constant. And, oh, I'm sorry, I was going to do D here. I'm going to put a D. I think that's what your book does. So, and D is the distance between the charges. So notice the change I made here. I'd written R, but your book uses D. It uses D really to differentiate between distance and radius, but the more common thing is to use R. But as for this class, we'll use D. It's just the distance between those two charges. Like charges attract. No, I'm sorry. Like charges repel. Then opposite charges attract one another. So if I have two positive charges, they'll feel a force that's opposed to one another. And if I have two negative charges, or a negative and a positive charge, those two charges will feel an attractive force towards one another. If you have multiple charges, there will be multiple forces. So take a moment. I want you to draw the force that is acting, say, on Q3. I want you to draw all the forces that are acting on Q3. For example, there is a force acting on Q3 that's due to Q4. Is it to the left or right? The force on Q3 due to Q4. Is it to the left or right? It's to the right because I have a negative and a positive. They're going to attract one another. So the force F3 due to F4 or due to Q4 is going to be in this direction. That is the force on particle 3 due to particle 4. Take just a moment to draw the other vectors, the other force vectors that are acting on that particle Q3. All right, so I have a force on particle 3 due to particle 1 up here. What direction is it going to be? Up or down? Up. And what about due to this charge? These two charges are going to be attracted or repelled from one another. They're going to be repelled because they're both negative charges. So if I draw my forces, the one due to that charge will be in that direction. I'll call that the force on particle 3 due to particle 1. And then the force on this charge, or rather due to that charge, is going to be in this direction. So that's going to be the force on particle 3 due to particle 2. You can't see that, can you? All right. These forces will become important. I'm going to calculate the force just to demonstrate, but you're not going to have to calculate forces. But they are important in how the body moves charges around. There are a lot of charges in the body that we use to send information to the brain and use for other purposes in the body. And so we'll use these electric forces to move those charges around as we need to. So just for example, let's calculate the electric force between two carbon atoms. Um, the charge of a carbon atom is plus 6e. And so that's 6 times 1.6, that's what, 60, what's 60 plus 36? 9.6 times 10 to the minus 16 coulombs. So a carbon atom has a charge equal to 9.6 times 10 to the minus 16 coulombs. And then I also need to know the distance. It's 0.5 nanometers. And so the distance is 0.5 times 10 to the minus 9 meters. And so if I want to calculate the force, I would say KQQ divided by R squared, D squared. K has a value of 9 times 10 to the ninth. I'm not going to ask you to calculate the force on any charges. I just want to show you that the force is actually quite big. The electric force is quite a big force. Times 9.6 times 10 to the minus 16 coulombs. But since there are two of them, I square that and then divide by 0.5 times 10 to the minus 9. And then that's also squared. That's the distance between them in meters. And this gives us a force of, you ready for it? It's a big number. 3.3 times 10 to the minus 8 newtons. That's not very big force, is it? Is that a big force or is that a small force? Big or small? That's a pretty small force, right? But when we're talking about very small masses, like the carbon nucleus has a mass of about 2 times 10 to the minus 26 kilograms, not 6, 26, 10 to the minus 26 kilograms, that force produces a very immense acceleration. Because you don't need, if you have such a small mass, you don't need a very big force to hold it together or to move it. And we could calculate that. We could say, well, F is equal to ma. And so the acceleration is the force, 3.3 times 10 to the minus 8, divided by 2 times 10 to the minus 26. And that's equal to about 26 minus 8, about 10 to the 18th meters per second squared. So we got these forces that act between particles, and they can produce an immense acceleration that can cause charges to move through the body with great force and or with small forces, but with great acceleration. It can be very efficient in moving our charges around. The body uses electric forces to move cations and anions around. All right, so which direction will these particles move? We'll do it as a clicker question. So A is right, B is left, C is up, D is down. The top particle, which direction will it move? Think about this particle. It sits in space, but it's surrounded on both sides. On one side by positive charges, on another side by negative charges. Those of you that have had anatomy know we're sort of leading up to the cell, and you get a similar thing with the cell when you look at charges that move back and forth between the cell membrane. Which direction will the top particle move? Will it move to the left, to the right, the left, up, or down in this area that's surrounded by other charges? All right, let's stop at 40, or 40, say 43. Okay, so these charges will move to the right. Down. Oh, I see what you mean. I'm sorry. Yeah. So, uh, what I meant was, is that we consider these two scenarios separate. Some of you put D, and that's sort of right, that this charge would be attracted to this charge. All right, but what I had intended that how do these charges respond to the charges on either side of it? I have a repulsive force from the charges on the left and an attractive force from the charges on the right. And so I get these charges will move to the right. So B is the right answer. And how about the next one? Yes, A is the right answer. It moves to the right. But what about for the negative charge? Which direction does it move? Does it move to the right, left, up, or down? And again, consider it as a separate situation. All right, so I will stop at 33. Okay, awesome. B is right. Uh, this charge is going to move in this direction towards the positive charges, away from the negative charges. Let's also think about this in terms of potential. We're going to define potential in just a bit, but let me go ahead and sort of give you a preview of potential because we'll talk about it in terms of the neurons and the cells and how they move charges around. Right, potential. You've heard of potential. Like you ask, what is the potential of that battery? And then you say, oh, it's 9 volts. That is a measure of the potential. Or you might say the voltage, and that's sort of a very similar word. It means the same thing basically. But potential is a measure, it's sort of a big idea, it's very important. Potential is a measure of energy per charge. Potential is a measure of energy per charge. And so when I'm talking about charged particles, they will move in directions of changing potential. Positive particles will move from high potential to low potential. So I would call this the positive side, the high potential side, and over here on the negative side, I would call that the low potential side. High potential, low potential. And so positive charges will move in the direction from high to low. Negative charges will move in the direction from low to high. I like to think of this as a mountain. You have a mountain, and then you put some ball on it. This is like my positive charge. Up here, I have lots of potential energy. So this is my high potential side. And down here, I don't have much potential energy at all. Because potential is a measure of energy per charge. It's very closely related to potential energy. So if I have a positive charge, it's going to move from the area of high potential to low potential. It's like it's going to roll down the mountain. Positive charges sort of do what you would expect them to do. But on the other hand, a negative charge, I have a negative charge on this mountain, because negative charges, they just sort of do stuff that doesn't make much sense. It would actually roll up the mountain. And so you can think about this in terms of our charges, that positive charges will move from high to low potential. They'll roll down the hillside, going from high potential energy to low potential energy. Whereas a negative charge sort of does the awkward thing where it moves up the mountain. We'll talk about potentials later, uh, but let's try these two clicker questions now. You need to think about your Coulomb's law, that KQQ over R over D squared, and how does the distance D affect the force on these charges? All right, we'll stop at 110. 110. 5 more seconds. Guess if you're not sure. A couple more seconds. Oh boy, okay, we're all over the page here. Let's see. So I have a force of 12 newtons. My F is equal to K Q Q over D squared. And I'm moving my distance D from 2 to 4 meters. So what I'm doing is I'm doubling my distance. That means that I'm going to quarter my force. So whereas my force was 12 newtons, now I'm going to divide that by 4, and it's now going to be 3 newtons. So A there is the right answer. Remember, that's our inverse square law. We're going to see that again coming up. We saw it with intensity, the power over area, and we'll see it also with Coulomb's law. That if I move to twice as far away, my force decreases by a factor of 4. If I move closer, then my force increases. By the way, have you ever thought about what holds the atom together, the nucleus of an atom? Because what's in the nucleus of an atom? Protons and what else? Neutrons, right? And so we have a couple of forces that are at work. We have an attractive force in the nucleus. What's the attractive force in the nucleus? Think about it. What are the two properties of matter? We have charge, and then what's the other property of matter? Mass, right. So we have charge and mass as a property of matter. The charge of those, the charge is going to produce a force that's attractive or repulsive between the protons and the neutrons. Will the protons and neutrons be attracted by their electric force, or will they be repelled by their electric force? All I got are protons and neutrons in there. Yeah, a neutron has zero charge, so they basically have no electric force at all. Well, are protons attracted or repelled from one another? They're repelled, right? Because I have two positive charges, like charges repel. Um, so there must be some force holding it together, because if a nucleus, if all it has is that electric force, it's just going to fly apart, right? Because it has this huge repulsive force in the electric force. Well, they have mass, so can the gravitational force, these objects also feel a gravitational force that is attractive. Is that enough to hold it together? You never thought about this? It's kind of a conundrum. Like, how do we hold that darn thing together? Because it turns out that the gravitational force is way too small. It's much, much too small. Right? If the gravitational force was big enough, then we'd be all sucked up into a ball here because we would have an immense force between us. But the gravitational force is much, much too small to actually hold a nucleus together. So we didn't mention this in the beginning, but there is a force. There are four actually fundamental forces, and we'll see this in the chapter on nuclei. But there are four fundamental forces. There's gravity, there's the electric force, then there's the strong nuclear force, and the weak nuclear force. And that strong nuclear force is actually what holds atoms together. There's another type of force that holds them together. All right, let's try this other clicker question. It seems like you're not all here today. Is it the time change or just tired? All right, let's try this one. I'm gonna wear my red nose and my clown paint on Thursday. Two positive particles experience a force that is which of these? I'm gonna stop at 20 at 30. Okay, awesome. It is repulsive. You have a repulsive force. You have two positive charges. They repel one another, just like the positive charges in a nucleus. They have a very immense electric force that are pushing them away. And so we have that strong nuclear force that actually acts to hold them together. Um, let's see. A neutron walks into a bar and he asks the bartender, says, "I'd like a drink. How much?" And the bartender says, "For you, what? No charge." Right. That's an oldie but goodie, right? And to be serious just for a minute, a life lesson too. Um, like we tell a lot of bar jokes, and that's okay because they're fun or whatever. And I know that sometimes you guys drink, but people have real issues with alcohol abuse, and so I I, I urge you to be responsible and to be uh, self-reflective about how you rely upon the consumption of alcohol, because sometimes people use it to sort of find an escape or to get away from the stresses of their life, and it can destroy your life. Seriously, I had an uncle. He died now, but he was an alcoholic. All my family are alcoholics. I'm sure that your family is too. You probably have a lot of alcoholics, but I mean his whole life was just about trying to find the next drink, and he would drink whatever he wanted. He used to go to my grandmother's house and drink like the cleaning fluid under her sink because he thought it would give him some. You know, y'all say, "Oh, that's repulsive," but I know that there are college students here at Nichols that are headed in the same direction. So don't let that rule your life, and it can rule your life. And you make decisions now that you know that set you up for that rule in your life. All right. I'm sorry. Let's do electric fields. Oh, no, I'm sorry, not there. Electric fields. And I'll let you out soon. I wanted you to do a little survey for me soon. But electric fields, two charged particles experience a force. If you remove one of the particles, the force no longer exists, right? That should be, you have to have two bodies in order to have a force. If I have two particles, they both experience either repulsive or an attractive force. But if I take away one of those particles, this particle no longer feels that force. It just sits out there in space with no force acting upon it. But something is there. And we use the electric field to describe that something. Fields, the electric field, we use E, is a measure of force per unit charge. It's typed there, but I'm just going to write it off to the side because it's kind of one of our big ideas. Potential is energy per charge. Electric field is force per unit charge. And we use this to just measure this. The electric field, we can calculate it, is equal to the force over the charge. All right, let me try to explain. It's kind of difficult to explain, but I have two charges here. They both feel a force. However, if I take away one of those charges, then I no longer have that force. But something still exists in the area surrounding this charge. Because I know that if I bring another charge in, it's going to feel a force as well. And we use this something that exists that is in some way related to the charge. We use the electric field to describe that. In a similar way, we use the gravitational field around the Earth to describe that something that's created by the mass of the Earth. But here, this something is created because of this charge, that I have this electric field surrounding this charge that we can actually calculate and measure. Now, if we place a charge at a point where there is an electric field, it will also feel a force, and that force is equal to Q times E. That just comes from this. I just solved it for F. So let's imagine I don't have this charge right here. There are no forces, but there is an electric field that surrounds this charge that has a value equal to E. And then if I bring another charge in right here, it now experiences a force that is related to that electric field, that's proportional to that electric field. The direction of the force is given by the direction that a positive particle would feel, I'm sorry, the direction of the field is given by the direction that a positive particle would feel a force. So for example, I can draw the electric field. I'm going to use these lines to draw the electric field surrounding this charge. Now, if I imagine that this is a positive charge and I bring in another positive charge, I ask myself, what is the direction of the force that this positive charge would feel due to this positive charge? And of course, you would say it would be to the right, right? Because they would feel this repulsive force. And so the direction then of the electric field is also going to be the same as the direction of that force. The force acting on this particle is in that direction, so the electric field is also in the same direction. And I can move this charge around, all around this other charge, and sample the direction of the force, and that tells me the direction of the electric field. All right, so let's try this, see if you can get this right. If Q is positive, what is the direction of the electric field at point A? Is it A up, B down, C left, or D right? Q is a positive charge. I want to know what is the direction of the electric field at this point. All right, I'm going to stop at 45, 45. Okay, very good. B is right. Uh, Tell me, what if Q was negative? I'll explain the first one in a second. But if Q was negative, what would be the direction of the electric field at point A? If Q was negative, what is the direction of the electric field at point A? All right, let's stop at 40. Stop at 40. Okay, good. C is right. It would be to the left. So if Q is positive, if I put a positive particle out here at point A, imagine like a test particle, it would feel a force in that direction. So the electric field is also in that direction. However, if Q is negative, the electric field would be in the opposite direction. Because if I imagine putting a positive test particle out here, then it would feel an attractive force. And so the electric field will be towards that particle. An electric field requires at least how many particles? One, two, or three particles? How many particles do you have to have in order to have an electric field? All right, we'll stop at, say, 38. 38. Okay, you only need one particle to have an electric field. So you need two particles to have an electric force, but an electric field you only need one particle. So I can have just a single particle out in space, say plus Q, and it's going to have an electric field surrounding it, even though there is only one particle. Now, in order for there to be a force, I would bring another particle in, and then it would react with this particle, and it would actually experience a force. So forces require two particles, right? And that's Newton's third law. But an electric field only requires one particle. But there is no force in the electric field unless there's another particle. All right, why don't we stop there? Oh, let's see. Hold on just a second. Don't put it away yet. Do we have other clicker questions on the next page? Now, we'll come back to this. I think y'all look sort of brain dead. But I do want you to do but you're not. I'm sorry, that was not nice. But you seem sort of bleh. Um, but I do want to do a mid-term assessment. So at the end of the class, you'll do an assessment. So if you could take out a blank sheet of paper, at the end of the class, you'll do an assessment, but you know, I use those to help change the course from year to year, but it doesn't affect you. So this is your opportunity now. If you have something that bugs you about the class, that you can tell me. On a sheet of paper, I just want you to tell me two things. What's one thing you like about the class that you would like to see continue? And then maybe one thing that you would change about the class. If you want to put your name on it, that's fine, but it's anonymous. You can make it anonymous. Uh, and I won't look at them as they come in. I won't know who put what. But when you're done, just maybe a sentence or two, one thing that you like and one thing that you change. And when you're done, just set it up here face down, and then you can go.